Talk about exponential functions. So chapter 7 is about exponentials and logarithms. All right? So you're going to learn a little bit about two of the keys on your calculator. That one has log for what's called the common logarithm, and one is ln, which stands for the natural logarithm. And so at some point in time during this chapter we'll be using them. And so exponential functions and logarithms go together, and then we'll also talk about what's called inverses, and that'll lead us from the exponential functions into the logarithms. So today we're just going to write and evaluate exponential expressions to model growth and decay. So our focus today is going to be on mostly just, first of all, what does an exponential function look like? And then how do I model growth and decay to be able to solve problems that involve them? So when we're talking about an exponential function, we're talking about something that's growing at a rate by a multiplication. Right? I was looking at another textbook recently, and they actually talk about sequences before this, just because there's a slight connection. They have them. Well, we'll be doing sequences later. But when we're talking about exponential, we're talking about just multiplying by the same amount all the time, like doubling. So for instance, we have this situation here where they have transistors per integrated chip, talking about circuits. Right? And to get from one value of transistors to the next, we're multiplying by 2. Right? And so all exponential functions is where we just multiply by the same amount each time. And it's always going to be a positive number. Okay? It might be a fraction at times, right? But it's almost always going to be a positive number. So you've worked with lots of exponents before because you know how to do powers. Right? And so we're going to look at it, though, as functions. Right? So we know that we have the base is the big thing on the bottom, and we have the exponent. And so most of the time when we look at functions, it's going to be in exponential functions, it's going to be in that form. But we have another form that we're going to add to this. Right? So f of x equals a times b to the power of x. Now this a that we have here is actually the same a, or has the same meaning and purpose as a did when we were working with quadratics. Right? This tells us that when x is 0, that a will be my y value. So it's my y-intercept in this case. But it also tells us about growth, or it talks about scale factor. So if I'm increasing by a certain amount or like that. Okay? So a does the same thing. And if it's negative, it means we have a reflection over the y-axis, or over the x-axis, vertical reflection. But most of the time we'll be looking at this, because a will end up being our starting value, which is usually where we cross the y-axis. Okay. So here's a graph of f of x equals 2 to the power of x. One of the most common ones that we use in math is 2 raised to the power of x. It just shows that we can see that as the graph moves from left to right, that it's growing at an increasing rate all the time. And we say it's an increasing rate because the difference from one value to the next is getting bigger and bigger. So like from 1/4 to 1/2, okay, so it's 1/4 bigger. From 1/2 to 1, it's a half bigger. From 1 to 2, it's a 1 bigger. 2 to 4, it's 2, and 4 to 8 is 4. 8 to 16 would be 8 more. So the amount that it changes each time from one value to the next is always getting bigger and bigger. So we say it's increasing at an increasing rate. Now we have also that when we have these exponential function here, like 2 to the power of x, you're never going to get a negative value. Okay? So this graph is never going to go below the x-axis. So we say that there's an asymptote on the x-axis. And what an asymptote is that as the graph gets closer and closer to that line, but it's never going to pass it. Okay? So, it might look like it does, but it never does. So if you're graphing an exponential function, don't ever go below the x-axis. If you do, then your graph is wrong. Okay? So the value of b, when b is greater than 1, we have exponential growth. So that would be like 1.5, 1.3, 1.06. And what's 1.06? When would that come into play? Test your knowledge right now. When would we see 1.06? You guys like to shop? Jake, you like to shop for shoes, right? All right. Not really?
Sales tax.
What? Sales tax, okay, exactly. All right. If you go out and buy something at a store, like yesterday, I went and bought a new pair of pants. I had a great deal at Kohl's. I had 20% off, and I had Yes to You rewards of $20. So I bought myself a new pair of pants for $4.23. All right. $48 pants for $4.23. They were on sale for $25. I gave them my $20 Yes to You rewards, knocked it down to $5. They took 20% off that, so now it was $3.99 then. And so when they calculated how much I owed them $4.23 because they took that $3.99 and multiplied it by 1.06. Right? The value of the price plus the tax. Right? So anytime we see a number when b is greater than 1, we have exponential growth. If b is between 0 and 1, we have exponential decay. So the numbers will get smaller all the time. Right? And the graph will look like, if we have exponential decay, then the graph will look like this. Okay? It will go that way. Right? So growth, it goes up as it goes to the right, and decay, it comes down as it goes to the right. Okay? All right, so graphing exponential functions. Now, we're not going to get into this real heavily because you have calculators, and we're going to use our calculators to do these, but it's important that you're able to see what the graph looks like. So go ahead and go to your y equals in your calculator and put in 10 times 3/4 to the power of x so that you can see what this graph looks like. All right, and go ahead and if we go and look at the table of values, here is our table of values from -2 to 3. So when you're graphing these on paper, which you're going to have to do a few of them, you might want a sheet of graph paper to make them more accurate. But we can see that as x is getting bigger, the change for the y value then is getting smaller. Okay? And it's getting smaller, and you'll notice that the difference between each one, that difference is getting smaller each time. And because that happens, it'll never actually get to 0. Right? So if I graph these points then, put those points on my graph, right? We can see that they are going down as they go to the right. And then if I plot the actual graph, and I can do this, y equals 10 times point. Let's see how good my skills are today. And not very good, apparently. Nope, that wasn't it. Well, we'll let it go for now. But if I graph this, all right, then the graph looks like this, coming down. And as it keeps going, it's going to get closer and closer to the x-axis, but never even touch it. Okay? So because the amount of change each time is getting less and less and less, it'll never actually get to be 0. And so if you went to your calculator and you went way down your table, that eventually it would probably say 0, but it never will actually be 0. Okay? So here we have decay because the value of b is what? Less than 1. Okay? So b is less than 1, so we have decay. Okay. So go ahead and put this one in your y equals, g of x equals 100 times 1.05 to the power of x. And let me...
X is 10. So
okay, so 100 times 1.05 to the power of x. Put our standard viewing window. Oops. And it's working, and I don't see anything. Okay. Why don't I see anything? All right, well, let's see. Okay, this says 100 times 1.05 to the power of x. Well, first of all, what does this number here tell us? Okay, it has growth. Okay, since it's growth, that means the graph is getting bigger, so it's going up as it goes to the right. Okay, but the big question is, what does that number 100 tell us? And the 100 tells us the y-intercept, or we could call it also the starting value, I like to call it sometimes. So it's like the starting value on the y-axis. Okay. So the reason you can't see it is because the graph is starting at 100 and going up from there. So if you look at it here, this one on my screen here, we can see that the y-intercept is 100 and it's getting bigger as it goes to the right. So how do I make it so I can see that on my calculator? Great. Yep, we want to go to our window and we want to change our y max. We need to go over 100. All right, so we'll say 200. Just take a look at what that does. Now when you do this, you want to change your scale also, just so like it could go to 10 if I wanted to. So the amount of marks you have, tick marks, are easier to see. Right. So there we go, that's a whole lot better. Okay, so we can see the graph is growing, it's getting bigger. So this is, but with 1.05, we only have a 5% growth rate there, okay? So it's not getting bigger real fast. Okay. And this one here, our decay rate is 25% or 1/4, right? So both of those numbers, when we talk about growth and decay, the growth rate and decay rate, they both work from 100%, okay, or 1. So since 3/4 is 1/4 less than 1, we say we have a 1/4 or a quarter growth rate there, or decay rate. Okay. We're down here because 1.05 is 0.05 greater than 1, then we have a growth rate of 5%. Okay, all right. So so the question is then here for this checking out, is this growth or decay? Is the value of b greater than 1 or less than, or between 0 and 1? So the value of b in this case is 1.2, so that means it's going to be growth. Okay, good. All right. All right, and then I'm just going to want you to put those graphs on paper, but here's the thing, I want them to be accurate. Okay? So you should always, if you're going to put this on paper, you need to show me your y-intercept and a couple points on each side of the y-intercept. Okay? So a couple of negative values, a couple of positive values. So if I did 5 times 1.2 to the power of x, right? Then you want to go to your table and at least include from -2 to 3, okay? From -2 to 3, those points should be somewhat accurately on your graph. All right, so you're going to have to plot some points. So this is not acceptable, okay? All right? And this is what some of you are going to want to do, but this is unacceptable, okay? Here's 5, and there's my graph, okay? All right, that's unacceptable, all right? It's got to be something where you actually have points, or at least approximate points, that you're going to graph to show me that that's where the graph goes, all right? From -2 to +3 at least. So you may want to use, when it comes to graphing them, you might want to use graph paper so that you have the most accurate graphs possible, okay? All right, growth and decay. So we'll start with growth. Here is the formula we're going to be using for growth and decay. And you'll notice that it has plus or minus in there because the plus is for growth and the minus is for decay. And the variables are very important for us. The a of t, and so we're going to be using a of t, or at least some function of t, because usually we're talking about time is our variable. The value of a, initial amount, okay, we talked about that already. It's the starting point or initial amount. And we have 1, because that's where everything starts with, 100%. And we either go up if we're increasing from 100%, or go down if we're decreasing from 100%. R is the rate of increase, and that is as a decimal. All right, so you have to change all the percents to decimals. Okay? And then T is time. Okay, the 1 plus R is said to be our growth factor, and 1 minus R is the decay factor. Right? So if we have growth, then we add that percent to 1. That's how we get to 1 plus R. If we have decay, we use the minus, and it'll be 1 minus whatever that percent is, the decay percentage. All right, so we've got our friend Clara here. She invests $5,000 in an account that pays 6.25% interest per year. Question is, after how many years will her investment be worth $10,000? So the first thing we're always going to do is write the function. All right. So we can always use a of t if you want, or you can, if the problem has something else that instead of using a, use some other letter to go with time, you can do that also. Okay? So in this case, I could say investment. So I could say this is I of t because we're talking about her investment over time. Right? The value of A, the initial amount that she has, is $5,000. So that's our value for A. Times 1 plus, and the interest rate, or the rate of increase in this case, is 6.25%, but we have to change that to a decimal, so 0.0625 to the power of t. So we're going to write an initial function. So this function that I've written has to do with this part here. Okay? She invests $5,000 in an account that pays 6.25% interest per year. This is the function that goes with that. then we're going to answer this question. All right? So it says, after how many years will her investment be worth $10,000? Well, the $10,000 then is this number here. So we want to know, when does 5,000 times 1.0625, how long does it take that to equal 10,000? So we're going to use our calculator. We will put the 5,000 times 1.0625 to the power of x. We're going to put that in y1. And we'll put 10,000 in y2. And we're going to find where those two things intersect, because we're solving an equation. So we'll find the intersection point. Okay. So y equals 5,000 times 1.0625 to the power of x. And then we want to know, when is it 10,000? So the first thing we need to do then is to what? Because if I graph it right now, I don't see anything. Okay, we got to change our window. All right. So the first thing we've got to do for sure is we have to change our y max. And here's the thing for you. Okay. Always, whatever this number is here, all right, that single number, that's always going to be your starting point to think about for your y max. All right. And you're almost always, y max is going to be a little bit bigger than that. Okay? Because I'm going to find an intersection point where this is part of it, so my y max has got to be at least that number there. Okay? And we usually want to go above it so that we can see when it happens. So when I go here, my y max, I'm going to make it something bigger than 10,000. Right? So we could go up to 15, we could go to 11. All right? Whatever number you want to use there, but something just a little bit bigger than 10,000, so I'm just going to make it 11,000. And I'm going to change my scale also just so I don't have as many tick marks on it. All right, so I'm going to change my scale to 10,000, which means I'm just going to have 11 tick marks on my y-axis, right? One for every 1,000. Okay, if we look at the graph now, all right, I can see there's my blue graph, and there's the 10,000, and the problem is, okay, we can't see it, so what do we need to do now? Okay, yep, we've got to change the x max now. We need to go farther to the right. All right, so where do we go? Well, from our graph, we could see it was getting close, right? So if we go 10 more, you think that would be enough? Well, what can we do? We can try it. If it works, great. If it doesn't, we go farther. Okay, so let's try 20. See what happens. Oh, that'll work because I can see it's higher than my 10,000. All right, super. So I can see I've made my window so that now I can see where they intersect. So now we do second, where? Second trace to find the intersection point. Number 5. And since there's just one spot where they intersect, all I need to do now is I can just hit enter 3 times. Okay? One for my first curve, which is the y1. Hit enter again for y2. And then hit enter again for the 3rd time for our guess. So what does this number stand for? That's our time. So our time is in years. So we are going to make a statement. Okay? So we've got 2 things here. We're going to say t with our answer. T is approximately 11.43 years. Okay, and we're making a statement. The investment will reach 11.4, oops, no, that's not, will reach $10,000 in about 11.43 years. Okay, but you have to write a sentence for me. Okay, if it's a word problem, I got to see a sentence. Okay. All right. Okay, good with that, right? Okay, let's do the decay one then. All right, so we'll go over here. Everybody got that one all right? All right, so here's a decay problem. City population, which was initially 15,500, has been dropping by 3% a year. So that dropping tells me it's going down. Write an exponential function and graph the function, and use a graph to predict when the population will drop below 8,000. Now your graph for this can just be on your calculator. It does not have to be, you don't have to draw me a perfect graph on paper, okay? On your calculator is fine. All right? So we need to know three things. We need to know A, we need to know what R is. And we need to know, is this growth or decay? Right? So this is going to be decay, so that means that when we use this formula, A of t equals A times 1, it's going to be minus R to the power of t, because we have decay. So we're subtracting the interest rate. Right? All right, let's see. So here we're talking about population over time. So I'm going to use the letter P instead of A, because we're talking about population. All right. Remember, A is the initial value, which in this case is 15,500. Times 1 minus, and it's dropping by 3%, and 3% is represented how as a decimal? Okay, 0.03. So we're going to have 1 minus 0.03 to the power of t. Okay. And when it says to write a function, I want this simplified. So the population over time is 15,500 times 0.097 to the power of t. All right, actually simplify it. And so when it asks for exponential function, all right, this is the one I'm looking for. I'm not looking for the one that has the minus sign. I'm looking for the one that's simplified. Okay. So there's our function, and now we want to solve. We want to know, okay, when is it going to be below 8,000? So we're going to solve this. When is it below 8,000? So when you graph this, you actually have two options for your y max, okay, on the graph. Could be 8,000, all right, because that's the important number, okay? Or maybe you want to see where it crosses the y-axis, the y-intercept. If that's the case, then your y-max is going to have to be all the way up to 15,500, all right? But we don't have to go there, because we only need to find where the intersection point is. All right, so let's look at it. Y equals 15 times 0.97 to the power of x. And 8,000. So if we look at our window, right? Our window goes, our max goes up to 11,000. That's bigger than 8,000, so that should work. We've got our x max is up to 20. That might be big enough. I'm just going to use that window then and graph it. And not quite. All right, so I can see part of it, but not enough. So we need to go to the right. All right. So let's make a bigger jump this time. Okay, let's go to 40. That's just a guess, whatever you want to. And I'm actually going to go above 15,500 so I can see the y-intercept. But you don't have to. All right, here it comes down, and all right, so that's big enough. So where do I go to find that point? Second trace, and intersection, number 5. And then we just hit enter 3 times for the first, for y1, y2, and my guess. So we get 21.71. So t is approximately 21.71. And do we have years again? Okay. So we will say, write a sentence, population will be below 8,000 people in about. Now, before I finish that, okay, I want you to understand 2 things that are acceptable here. One is, I want to see this number, okay, t is approximately 21.71, but the population will be below 8,000 people in about 22 years. Okay, why would I use 22 years instead of 21.71? Because if somebody's going to be doing any testing of this and actually checking it, are they going to check it in as partial years, or are they going to talk about full years? Okay, they're going to talk about full years. So you should show me this, all right? But then when you write it, you can write it as a whole number rounding up, okay? Same with the other one. We could have given just the decimal number in our solving of it, but then when we write our statement, we could have said the full, a whole number, okay? All right.